All right, so here we go, section 5.2. The title of section 5.2 is area, but that really doesn't give you much insight into what we're doing. We're going to talk about finding the area under a curve on a graph. All right, so our objectives are to use sigma notation to understand the concept of area as it is being used in calculus, approximate the area of a plane region, and then to find the area of a plane region using some limits. There you go, limits. Remember limits from a long, long time ago? Well, they're back. They're back to bother us again. Now, first off, throughout the session, and again, for a lot of Calc 2, you are going to be using the idea of sigma notation to concisely write out summations. So just to review, hopefully you've seen this before. It's supposed to be done in college algebra and pre-calculus, but some of you may have had kind of a spotty exposure to it. So hopefully you've seen this before. If not, we'll try to get you up to speed pretty quick here. Sigma notation is a way to write out summations. All right, so first things first, a sequence. A sequence is an ordered list of numbers, ordered list of values. A sequence could be something really simple like 2, 4, 6, 8, and so on and so forth, whereas this is just referred to as an arithmetic sequence because we're adding 2 each time. Right? The elements of a sequence are designated by their location within a sequence. So like I could say that this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, because the 2 is the first term in the sequence, the 4 is the second term in the sequence, the 6 is the third, the 8 is the fourth. Now before someone gets all upset, yes, sometimes we start sequences and call the first term the 0th term. I understand that some computer science does that because something about arrays and arrays starting at 0. But my understanding is that that is, while acceptable, not how we're going to do it here. We're going to start our sequences calling the first term the first term, not the 0th term. If I have a bunch of candy in front of me and I start counting out pieces, I don't call the first piece 0. I call the first piece 1. So the first term is 1, second term is 2, third term is 3, and so on and so forth. Okay? When you add up terms of a sequence, so if you do this, 2 plus 4 plus 6, now you have a series. A series is the sum or the partial sum of a sequence when you add up some of or all of the terms. Right? You can have an infinite sequence, you can have a finite sequence, you can have an infinite series, you can have a finite series. Okay? But if I want to add up a bunch of terms of a sequence, it'd be nice to have some convenient notation, some operators that tell me to do that. And here's where sigma notation comes in. Right? Sigma notation says that if you want to take the sum of the first n number of terms, where n can be anything, so n can be 10, 20, 50, 1,000, a million, whatever, the notation that we're going to use is this notation right here. Now the reason it's called sigma notation is because this is the Greek letter sigma. Right? We have a general term formula over here. This is a formula that we use to generate the terms of the sequence. This is our index variable. Okay. This number 1 right here is our lower bound. And this n up here is our upper bound. Now, you don't have to start with 1, but we usually do. We usually start with the first term. There's no reason why you couldn't say, okay, well, let's start by adding the 5th plus the 6th plus the 7th plus the 8th and go out to the 12th term. Okay? But we usually start with the first one because that's what we're usually doing. Okay, so we're doing summations. A summation, a series, a summation of a bunch of terms of a sequence. Right? We have the index. I is our index variable. A sub I is the ith term of the sum, or the general term for the formula for the sum. And we have upper and lower bounds. So we're adding a bunch of things together. So for example, our example here is to find the following values for the sigma notation examples. My job here is to do a summation. How do I know it's a summation? Sigma says do a sum. Start with the first term, because I starts at 1. Stop at the 6th term, because the upper bound is 6, and add all those up using the formula I. So when I is equal to 1, the term of the sequence is 1, plus when I is equal to 2, plus when I is equal to 3, plus when I is equal to 4, plus when I is equal to 5, plus when I is equal to 6, and stop because I have achieved my upper bound. And now I just add these things up. Okay? So it looks like that's what, 21? 2 and 3 and 5 is 10, 6 and 4 is 10, 10 and 10, 20 plus 1, 21. So I added them up, I get 21. So basically what I'm saying here is I've got this notation that I'm going to be using a lot for the rest of chapter 5. And I'll be using it again when I get into my Calc 2. It's summation notation. Right? All right, so here's another example. I know I'm doing a summation. I got my summation. I know that I'm starting with 1 and going to 7. I'm starting with the first term and I'm going to the 7th term. And my formula to generate the terms of the sequence is going to be the formula I squared. The nth term formula is I squared. So that means I'm going to do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared, and stop because I have achieved my upper limit. And now I'll clean this up. This is 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. And now I'll add them up. Let's see, that's going to give me 50. Let's see, 9 and 16 is 25. 25 and 25 is another 50. 36 and 4 is what, 40? So 140. Okay, so I added them all up. I found the value of this summation. Find the value of a summation. 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4 plus 1 over the square root of 5. I think that's going to be 3 halves plus 1 over root 2 plus 1 over root 3 plus 1 over root 5. This is 1. This is 1 half. 1 plus a half is 3 halves. The other ones are ugly. I'm just going to leave them. If you prefer, if you'd like, we could rationalize everything and then find a common denominator, but I would just argue that it's not worth it. Okay? Summation, lower limit, upper limit, formula. Start at 1, go to 5. Summation. Now this one's different. This one's a little more complicated, so I want you to take a look at it for a second and see what's different about it. Right? Now I'm hoping that you're seeing the same thing I'm seeing. Do you see that? Yes, it's a summation, and yes, I have a lower limit and I have an upper limit, but I'm hoping that you're noticing that there's 2 different variables in this expression. That is not a typo. I did not make a mistake. Right? We are making the argument here that n is just unknown. And so I've got 1 over n times 2 plus 5 plus 10 plus 17, right? 2, 2, 5, 5, 10, 10, 17, 17, okay? 1 over n times whatever that adds up to. What is that going to add up to? 10, 20, 32, 34? I get 34 divided by n. Okay, we good? Since the summation variable is I, I is the only thing in the formula that changes. I don't know what n is. And since I don't know what n is, n stays n. The only thing that's changing is the I. Okay? All right. Now, we are going to be doing some summations, though, where the ability to brute force these and to grind out solutions by simply adding them all up will not be sufficient. Right? This is fine. Doing it this way is fine if it's 6 or 7 or 5 or 4. But would you want to do this? Would you want to do the summation as I goes from 1 to 100? 1 to 100 of something like 3i plus 6? Because I've got to write out 100 terms, figure out the value of all 100 terms, and add them all up. Now, me personally, I don't want to do that. That sounds like work, and I'm lazy. Right? And because I'm lazy, I'm always looking for a better way to do it, a faster way to do it, an easier way to do it. And that's what's going to happen here. These are going to be some summation properties that we are going to be able to use to simplify, to quickly simplify, and to quickly work through some of these summations. Now, the first two are just some simplifications where we take a summation and write it in a simpler form. So we'll take a look at this one on the left over here. And it says that if you are given a summation where the formula for the summation terms contains a constant k multiplied by every single term, that if you want to, you can pull that k out in front of the summation and deal with it later. Now, we kind of did this already. We did it right here in this one. Okay? We could have looked at this 1 over n and said, that's a constant that's going to be in every term. So I could have rewritten this as 1 over n times the summation as I goes from 1 to n of I squared plus 1. And it's essentially what we did right here on this step where we factored out that 1 over n from every term. Okay? Now, the reason that I would do that is because maybe if I make this simpler, I can evaluate it more quickly. And so I can use this to simplify my formula for my terms. And if I can simplify my formula for my terms, then what I can do is I can make it happen, or I can evaluate it more quickly. Same thing's going to happen here. I've got a formula that says if I have a summation where the argument of the summation, or that general term formula, is the sum or difference of two sequences, then I can just rip it apart and write it as two summations. Now remember, though, these are equal signs. Oops. Wrong way. That's an equal sign right there, which means the left can turn into the right, or the right can turn into the left. That if you had two summations and you wanted to write it as one summation, provided that lower limits were the same and upper limits were the same, you could always take two summations and write it as one summation. Right? So what's happening here is I'm looking for ways to get summations done more quickly. These first two properties we looked at up here are simply properties that deal with simplifying a summation, okay, without removing the summation. Okay? There was a sum over here on the left, there's still a summation. There was a summation, now there's two. Right? So the summations are still there. These formulas down here, though, are going to be formulas that remove the summation. Okay? Our first formula says that if your summation is always just a constant, then it's just the constant times n. Now you might be looking at it going, I don't understand. What if we had this? The summation as I goes from 1 to 5 of 2. Well, the formula says that the terms of the sequence are always just 2. So when I is 1, 2. Plus when I is 2, 2. Plus when I is 3, 2. Plus when I is 4, 2. Plus when I is 5, 2. And how many 2's is that? I gave it away there. There are 5 of them. So that's just 5, the upper limit of the summation, times the constant, 5 times 2, 10. Right? Now, the other thing I hope you saw there was, this is a formula that removes or gets rid of the summation and replaces it with a different formula that we can quickly calculate. The same thing is going to happen here, here, and here. And basically what 2, 3, and 4 say is if you can use these properties up here to simplify your summation down. So all that it is just plain old I in number 2, plain old I squared in number 3, or plain old I cubed in number 4, that you can then quickly calculate it by using the formula here, here, or here. Right? Now, this is not to say that these are the only summation formulas that exist. This is just simply to say, here's 3 of them that you're probably going to see again. I definitely know that you're going to see number 2 and number 3, number 1, number 2, and number 3 again. You'll probably see number 4 also. Right? These are just formulas that we can use to simplify a summation. Okay? All right, so I have a whole bunch of examples here, but we're already at 16 minutes. Actually, I shouldn't say a whole bunch of examples. I just have 2 examples. So we're already at 16 minutes, but this changes gears down here. So what I'm going to do is I'm going to do these 2 examples, and we're just going to end up with a little bit of a long video. Okay? All right, so here goes. My job is to evaluate this. I'm supposed to find the summation as I goes from 1 to 36 to 3i plus 1. Now I could brute force this thing and write out all 36 of these and add them up, but I really don't want to do that. So what I'm going to do is I'm going to use all those properties we just got done looking at to rewrite this in such a way that I can get it done quickly. So my first step is to rip this thing apart using those first 2 properties. And those first 2 properties tell me that I can rewrite this as 3 times the summation as I goes from 1 to 36 of plain old I plus the summation as I goes from 1 to 36 of 4. Okay? So what I'm doing here is I'm using these 2 properties right here. Okay? This one says pull the coefficient out. This one says rip it apart at the addition symbol. Now that I've got 2 summations, I'm going to use the properties from this box right here. So first thing I'm going to do is I'm going to clean this mess up because I was doing a lot of scribbling all over it. And I'm going to make the argument here that I can use rule number 2 here, and I can use rule number 1 here. Okay? Just a constant, just a constant. Plain old I, plain old I. Right? So this is going to give me 3. And then what does I turn into? I says it becomes n times n plus 1 divided by 2, where n is our upper limit of summation. Right? Whatever that upper limit is. So it's n, 36, upper limit of summation, times n plus 1 divided by 2. Plus, and this addition symbol is this addition symbol. Now I'll move to the second summation where I'm going to use property number 1 that says if it's a constant, it's just the constant times the upper limit of summation. All right? Doing a little bit of math here, it looks like I've got 3 times 18 times 37. Okay, if you're wondering where 18 came from, 36 divided by 2. Plus 4 times 36. Let's see, 3 times 18 times 37. I can do a lot of stuff in my head, but I'm just not feeling it right now. So 3 times 18, got my calculator, times 37. That's 1,998. Plus 4 times 36, 144. And I get 2,142. Now, had I written all 36 terms out, it would have gotten the same answer. It would just taken some time. Okay. All right. Our second example. Same idea. I've got a summation, and I want to simplify it so I can do it quickly. Now, 10 isn't that big of a number. I could probably just write all these out. It wouldn't be that bad. But I want to get in the practice, so I'm going to use them. First thing I'm going to do is I'm going to use those first two simplification rules to turn this into 2 times the summation as I equals 1 to 10 of I squared plus the summation as I equals 1 to 10 of I. Now, as a useless note, you'll notice that I don't put these little things on the end. I don't spend a lot of time drawing my summations. If you feel the need to make it look more like this one over here by doing that, go ahead and do that. Knock yourself out. Okay. All right. Now what I'm going to do is I'm going to use those summation formulas. I know that this is number 2 and this is number 3 from my rules over here. So I'm going to use those 2 rules to make this thing work. Okay. So this shouldn't be too bad. I think I can do this. Let's see, I squared. So this is going to be 2 times I squared is n times n plus 1 times 2n plus 1 divided by 6, where n is the upper limit of summation. So it's going to be n times 2n plus 1, right? Oh, I got them out of order, sorry. N times n plus 1 times 2n plus 1 divided by 6, okay, plus, and that's this addition right there, I just did that one, so I know that one. It's n times n plus 1 divided by 2, where n is the upper limit of summation. Okay, now I just got to go through and clean this mess up. 2, 3. Let's see, 2 times 10 plus 1 is 21. So that's going to be a 7, and that's going to go away. So it looks like I've got 10 times 11 times 7 plus, let's see, 5 to 55. So 770 plus 55, 825 is my summation. And there we are at 22 minutes. Okay? Now, that brings us to the end of this video. I'm going to toss something in here on the end. Feel free to not listen to this if you don't want to. It's the story behind this summation formula. All right, so here's the story. Carl Friedrich Gauss, mathematician back in the day. If you remember back in grade school when your teacher used to give you busy work, you know, a worksheet just to keep you quiet, just to get you to shut up for a while where they had to go do something. And it was usually something that just was pretty easy to do but took a lot of time. Well, the story goes that he was given the assignment to add up the first 100 integers. And the teacher's expectation was that this will take some time and that busy work will do its thing and students will stay busy. Well, a few moments later, Mr. Gauss, young Mr. Gauss, walks up with the answer. And so when asked to explain it, he said, well, it's relatively simple. If you take and line up the same digits backwards, and then take the sum of these two series, you get 101 every single time. And because he knew that in this summation down here, that there were exactly 100 terms, he knew that this sum of the green line, which is all that he wanted, would be 100 times 101 divided by 2. The reason you're dividing by 2 is you don't want the green line and the gray line. You just want the green line, so you only want half of these numbers. And so he was very quickly easy to say, well, that's just 50 times 101. 50 times 101 is 5,050, so that means that 1 plus 2 plus 3 all the way up to 100 is 5,050. And then he generalized it out and got this formula that we have up here. So the formula n times n plus 1 says that if you add, it's 1 plus 2 plus 3 plus ... plus n. When you write it backwards, it's going to be n minus 1, n minus 2 all the way down to 1. But every single one of these pairs, excuse me, always adds up to n plus 1. And there are n of them, and divided by 2. I think he was like 8 or 9 at the time when he came up with this, which is impressive by anyone's standards. All right, that's the end of 5.2 part, that was part 1, right? 5.2 part 1, we'll come back and take a look at area and how these two things connect in part 2.